Welcome, everybody. My name is Dan Weeks, and today I'm going to do a brief introduction to Apache Iceberg. It's going to be kind of a high-level overview of a few specific features, and then I'm going to hand it over to Chunshu, and he's going to talk a little bit about the Presto Iceberg connector. So what we're going to cover first is just a little bit about why do we need Iceberg? What is Iceberg? Where does it fit within this ecosystem? Then we're going to go through a few select features, and then finally end on a couple takeaways drawn from a couple of the discussion points that we have. So first thing is, why Iceberg? Where does this fit within the larger big data ecosystem? Why do we have it? Why now? And in order to understand this, you actually need to go back and think about like how this entire ecosystem evolved to some extent. At the very beginning, you had MapReduce, and that was built around the idea of a distributed file system. And at the time, the challenge was really around like, how do we process these data files, log data, really unstructured. But the challenge was really on the side of the engineering around distributed data processing. And at the very advent, there wasn't a lot of attention paid to the actual structure of data. You can see that with just like files strewn around in directories. The effort put into this space was largely focused on how do we build systems that can process data faster, can process bigger data. And it was less around the integrity of that data and really having good semantics and guarantees about it. Now, over time, that's evolved considerably. We've gotten rid of a lot of the real primitives of like writing Java-based MapReduce code. We've got SQL abstractions on top of that. The processing space, like with Presto, has gotten really complicated, but there are still a lot of deficiencies in terms of how we think and represent the underlying data. So when we think about data, at the very advent, it was really about how do we just process this data? How do we parallelize it? But now the industry has gotten much more mature, and we have new fields of data science and analytics that are being done on this incredibly large trove of information. And we actually need to think more about the data itself. And what we don't want to be thinking about is files. And this is something that we're going to see repeated throughout as we go through some of the features. But a lot of how we actually work with data is just a manifestation of the physical representation that we've had for years up to this point. So when a data scientist sits down, they probably don't really care so much about what is the underlying file system, what is the structure of that data. They actually want to be focused on extracting value from the data and thinking about the data set as opposed to the actual files. So why Iceberg and why now? Well, a big part of this is the idea of bringing in an open format. Rather than solving this challenge in bespoke different ways across different solutions, you actually want an open representation of data that can then be used across lots of different systems. There are lots of good reasons why Iceberg was built for performance, scale, cloud native, but ultimately the main component of this is that you have an open standard for how to represent and access data. So with that, let's jump into a few features of Iceberg. So one that we talk about quite a bit is schema evolution. And this isn't really a new concept. This is something that every system talks about to some level, but largely in the big data ecosystem, we've kind of shied away from really working or accepting schema evolution because it's hard. And the challenge there is really that like everything supports some small amount of schema evolution, but the rough edges are really prominent and can cause massive damage to data sets and take a lot of time when things go wrong. So largely this is avoided. Well, Iceberg takes a different approach to this and really intended to solve the challenges around evolving schemas. So initially, when you're building data sets, you think about data and you say, well, evolution really isn't important. I'm going to spend my time like designing this data set well, getting the structure correct, and we don't need to worry about evolution in the long term. It'll be fine. And a lot of times you start out with very small data. And so if you do need to restate, that's not really a big problem. However, it is really important over the long term, 3 months, 9 months, a year down the road, maybe 5 years of data that you've curated. You eventually will need schema evolution. And it may be that you need to introduce new fields to a data set. It may be that you realize something needs to be corrected that was misrepresented in the data set. And once you have large amounts of data, this becomes really challenging, and it can suck up a lot of time in order to restate data, migrate tables. And with systems that don't fully support this, you're faced with some really bad scenarios. If you go to do schema evolution without full support for it, like your best case scenarios are like it just breaks immediately and you realize that there's a problem. You go in, you roll back those changes, you fix whatever is going, whatever the problem was, and nobody really notices. And you resign yourself to, okay, we're going to have to create a new data set. We're going to migrate all of our data into this new data set. And there's a huge, coordination effort that goes on. In the worst case scenario, you actually end up with inconsistent behavior across different systems. It may actually look like the schema change took effect, but then when somebody else goes to access via another mechanism, another engine, maybe export the data to other systems, you realize that something's not right. And even in that case, the best scenario is that you realize that at that point, but correctness issues can emerge, and it can be as simple as something like introducing null columns where something was projected incorrectly. But the more insidious cases are where you actually run into a challenge where the data actually looks roughly similar, and then you're operating off incorrect data. And once you find out that there is a problem, now it's a much harder situation to unwind. Like you have to get in there and figure out like, where is the good data in your data set? How do we reconcile this and migrate it into a good format? So the challenges here are pretty significant, and largely we've kind of emerged with this sense of learned helplessness, where we know not to go and evolve schemas of tables, but we need to change this. Like we cannot continue to just restate everything anytime a small change is necessary. So Iceberg addresses this by tracking the actual columns by identifier. Most systems do this projection by name or by column ordinal. Iceberg actually went through the effort of kind of fixing this and then making sure that we can provide strong guarantees. And that includes safe type promotion. So if you want to go and change your string type to an integer type, that's really not a safe operation. And if you go back to what we had talked about originally, the files and messy data that we had before, that was just kind of accepted. But at this point, like you get different behaviors from different systems. Like you may get nulls in one case, you may get truncated data in another, and you may see exceptions thrown in another. So you don't have a lot of confidence if you're going to make a change like that, what the net result is going to be. And then lastly, and of more importance recently, is some of these schemas are getting really complicated, especially in some of the more niche like data science and machine learning type use cases. You may be representing sparse matrices that have arrays of structs, and you need to introduce a new metric or something like that deep down in that nested structure. And Iceberg supports that as well, safely. So many different systems have some concept of schema evolution, but that doesn't necessarily mean that it's really a safe operation. We expose a lot of those rough edges to users who are in many cases new to this space, and that really shouldn't be the case. So Iceberg addresses those challenges. The next thing I want to talk about is hidden partitioning. And again, this touches back on the original point of, hey, we're thinking about files in addition to our data. And hidden partitioning is the concept that we can actually use values in the table to represent the physical structure. We want users to be thinking about the data in context of the actual data set and not the underlying representation or layout within whatever kind of file system happens to be supporting it. So we want to think about data and not the structure. So partitioning is a good example of this. And just to give a concrete example, if you're an analyst or somebody working in the data space and you sit down and there's some operational issue going on, and you want to say, hey, we just need to look at the events for the last 12 hours. Naturally, you would think, I've got a data set, it's got a timestamp field for the event, like I would just write a query against this. But that's hugely problematic because guess what? That actually produced a full table scan. And this is where a lot of the data modeling gets mixed up between the actual intrinsic data of the data set and the physical layout. So when you think timestamp, well, that is just when the event occurred, but the partitioning, whether it's aligned with that timestamp or not, is actually in different columns. And that's purely a representation that's just poked up from the file system all the way into the user schema that users have to care about. And what they really wanted to do was add a partition filter as well. Now, this gets really complicated if you're looking for ranges and your table is partitioned by hour and day, and you're trying to make sure that you capture enough data to align with the timestamp field. So if you've had to struggle with this, you know how complicated it is and that it's not really intuitive to users of data, especially if they don't understand the physical layout. In Iceberg, this is addressed by actually creating physical partitioning based off of the data values in the data set. So we introduced transforms. So in this case, it's a day-hour transform on top of the timestamp field. So a user can actually just run this query and Iceberg will figure out with great fidelity which files should be included in that scan and which should not. So this handles both that kind of logical concept of what's in the data set as well as the actual physical representation, kind of breaking us away from those early thoughts of like, hey, everything is really tied to the actual physical file system and data files. The next topic I want to cover is indexed metadata. And this is more related to performance and scalability within Iceberg. And the idea here is really that we do a lot of pruning at many different levels within the Iceberg metadata structure. And there's a lot of talk about improving performance of engines and making data processing faster, but the best thing you can do to improve performance is process less data. You can have the fastest compute operators in the world, but if you're doing it on less data, it is going to net be faster. And this is a challenge that, for data sets that are getting into the petabytes, tens of petabytes and beyond, you need an indexed structure in order to effectively work with that. So when you think about how Iceberg approaches this, there's all of these different layers within the indexed metadata. The first one being just snapshots, kind of separating current data from historical data. So the difference between what is the current state of the table versus time travel queries. And then you go to the next level of the manifest lists, and you can decide, hey, which manifests am I actually going to process, which has relevant data for me. You go down to the next level of the actual manifests, and we use statistics there as well, pruning further. And then you get to the files. And of course, we leverage some of the features of Parquet and Orc and other things to identify which row groups and which column projection. But the important thing is you've got this tree structure that you can navigate, and this allows you to scale your data sets really effectively. The other thing that you can do with this, and is somewhat distinct to Iceberg as well, is that you can actually pivot that metadata in different ways for different kinds of use cases. So if you have a bucketed table and you have point lookups, you can actually pivot your metadata to align with that. So you get, second level query over petabyte size data sets. And that really makes a very powerful kind of index over your entire data. So as I end here, a couple key takeaways. Like Iceberg is really designed to improve productivity of users. You shouldn't really be thinking about some of those physical constructs, and we can abstract those. Performance and scalability was also a real focus in terms of being able to be built on top of object stores, as well as leveraging that index structure in order to scale up data sets to immense sizes. And then the last thing is Iceberg is that open standard. We have cross-compatibility across lots of different engines. And ultimately, you don't want to be taking your data and copying it from place to place to place just to work with it. You want to be able to point at a single source of truth and leverage that data across anything that can interact with it. With that, I'm going to go ahead and say, please join us in the community. There's actually a Slack channel, pretty active, a lot of people hanging out, asking questions. If you do have any specific questions, great place to go. There are also some really good YouTube videos by Ryan Blue, if you're interested in deep dive into some of those metadata-based optimizations and understanding how the mechanics of that actually work. With that, I'll hand it over to Chunsu so he can walk us through the Presto Iceberg connector.
Sure. Thanks, Daniel, for your nice presentation. This is Chunxu from Twitter. And what we'd like to do next is to continue the presentation with more introduction about the Presto Iceberg connector. Okay. Yeah, so good morning, good afternoon, good evening, and good night, everyone. This is Chunshu Tan from Twitter. So here I want to talk a little bit more about the Presto Iceberg connector. So there are mainly three parts of the presentation today. The first part is that I would like to talk a little bit about the Presto at Twitter. And then I will introduce the design of the architectures of the Presto Iceberg connector. And then I'll show you folks some examples about how to use the connector. So let's begin. First is about the hybrid cloud Presto federation system at Twitter. At Twitter, for nowadays, we are maintaining a few Presto clusters across both on-premises and the cloud, which is the Google Cloud Platform. And we are serving requests from notebooks and BI tools. Those tools will first send their queries to a Presto router service, which will then forward the request to different clusters based on the requirements. And at the same time, we have a query cost prediction system, which is where we have applied some machine learning techniques to help us to predict the resource usage of each Presto SQL query. In that case, we can more intelligently schedule the queries across different clusters. And those Presto clusters usually will talk to the data storage and the metadata storage across both on-premises and the cloud. So that's mostly about the Presto at Twitter. That's about the federation system. And then the next question is that like why we want to have like Apache Iceberg at Twitter, and what are the features we really like? As what Daniel has just talked about, the Iceberg itself is an open table format for huge analytic data sets. It has some really nice features like schema evolution, hidden partitioning, partition layout evolution, time travel, version rollback, etc. And also, as what Daniel has just mentioned, like we should think about when we think about data, we should not just think about files, but say what else can we think about how to organize these data sets, right? So why we want to have Iceberg at Twitter is that we also would like this nice feature to transition the data lake from files to tables. So suppose that we have like ORC files and Parquet files, and we want to have like different query engines like Hive, Presto, or Spark to query these data sets stored in these files. These are just the files, right? But we want to have to organize them into, for example, some tables. That's why we would like to apply Iceberg in the middle layer as an extra layer between the query engine and those files. In that case, it can help us to organize the data sets into some tables, and then say we can just use Presto, for example, with the Presto Iceberg connector to query the data sets and get some really nice features like tables. Especially there's a very nice feature that we are using now at Twitter is about the schema evolution. At Twitter, we are maintaining lots of data sets, and we have observed that as the time goes, the metadata of these data sets are not immutable, which means that as the time goes, we always have some like requirements to modify the metadata of these data sets. Like for example, we may want to add a new column or drop a column or rename a column, etc. These are some very nice features that has been provided by Apache Iceberg. And that's why we contributed to the Presto Iceberg connector and apply it at Twitter. Here, I just want to give you folks a quick reminder of the format which Daniel has described about the Iceberg. That in Iceberg, there are different files, different structures like snapshot, manifest list, manifest file, partition spike, tuple, snapshot log, etc. And then here, I want to show you folks some simple examples which are generated from the Presto Iceberg connector, hopefully to give you folks some more ideas about what the structures of these files are. So here are three files generated from the Presto Iceberg connector on the TPC-H benchmark. Here it is the customer data set. So there are three files, manifest list, manifest, and table metadata. For manifest list and manifest, those two files are originally in Avro format. To make them a little bit more human readable, we convert them into the JSON format. So here, for example, for the manifest list, it has like say different key value pairs, like the manifest path, length, partition spike, snapshot ID, etc. And for the manifest, usually it may refer to one or more data files. For example, here there's some fields like status, snapshot ID, data file, etc. And for the data metadata, which has already originally been written in JSON, it is used to describe the metadata of a specific table. Here, the table is the customer, which has, say, there's three columns here, like the region key, name, and comment. And there are also some like relationship among these three files that construct the whole structure of the Iceberg table. So for example, there are some like the two green blocks here in the manifest list and the manifest. It is about the snapshot. In the manifest list, there is a field about the snapshot ID, which is exactly the same as the green block in the manifest file. And also in the manifest list, there's a like red block, which is about the partition spike ID. And then in the table metadata file, there's also a partition spike ID field here. And also for the manifest file, there's like a data file key, and there's a file path and file format, which indicates that the real data set, the real data is stored in a Parquet file. So that is some examples of the Iceberg table generated from the Iceberg Presto Iceberg connector. So for the next part, I want to talk a bit more about the design, the internal design of the connector. So the main idea is quite similar to other connectors in the Presto ecosystem. Here, I would like to talk about the write path and the read path. For the write path, the very simple command here is a CTAS that we want to create a new table as select. So here, first step is that we'll load the data set from the source, which is the data set that we want to select from. And then the next step that we'll write some metadata into a metastore. Previously, the metastore here means the Hive metastore. But as with one of the current projects implemented by Jack Ye from AWS, we also would like to offer another option, which is a native folder stored in HDFS, which will help us to remove the dependency of Hive metastore. So in that case, which means that for the step 2, we can write metadata to Hive metastore or another native folder in HDFS. And then the last step is that we'll write the data files into a data thing, which could be, say, HDFS or GCS bucket. So that's about the mechanism for the write path. And then in the read path, the mechanism is quite similar. It is that we'll first need to load the metadata from the metastore, which could be, say, a Hive metastore or a metastore in a HDFS as a native folder. And then we'll load the real data files from HDFS or GCS buckets. So that's the major like architectural design of the write path and the read path of the connector. So here, the next step is that I want to show you folks some examples about the Presto Iceberg connector, like how we could use it to get some really nice features from Iceberg tables. So here, the first example is about how to create a new table. So it is actually the CTAS commands, a create table as select. So here, all the examples here, what I'm showing now are written in Zeppelin notebook. Zeppelin is a web-based notebook service, which is quite similar to Jupyter notebook. So in a Zeppelin note, what we can do is that we can just write some like SQL statements and then assign an interpreter to it. For example, the interpreter is a JDBC interpreter pointing to the Presto Iceberg cluster. And then we can just run the SQL statement that we have written in this paragraph and get the results. So here the two commands are that we want to create some new tables from the TPC-H nation dataset and the customer dataset from the two datasets. And then we can just use the Presto Iceberg connector to achieve that. And then here are some we can run some query against the two new tables that we have just created, which is about the customer and the nation tables. So here I ran a inner join SQL statement across the two newly created tables. I joined by the nation key column and then get some corresponding results here. So you folks can see that we can really get some results from the two tables that we have just created from the Presto Iceberg connector. And then the next example is that we can also insert some new rows into Iceberg table through the Presto Iceberg connector. For example, here I want to insert a new row into the newly created nation dataset. And the values here is 25 is a nation key, new country is a name of this country, and 1 is a region key, and comment is just the comment field. And then I can run a select from statement to query the result. And the query result is shown here. So it is about the new row that we have just inserted into the table. And then there's something about the schema evolution, which is a really nice feature that we are using now at Twitter. So the idea is that I put two examples here. One example is that I could add a new column to the newly created table, and then I can also drop the column from the table. So here I ran an alter table statement, which is adding a new column named zip into the newly created nation table. And then I ran a describe SQL statement to get some information about the columns. So here you see there's a new column named zip here, right? And then on the right side, what I can do is that I can run an alter table to drop the column zip from the data set. So see here, the column has been removed. So that's about some of the nice features of the Iceberg. And also finally, there is some ongoing work that we are doing now in the whole open source community that I would like to share a little bit about it with you folks. The first one is the native folder support for metadata storage implemented by Jack Ye from AWS. This will help a lot about offering an option to remove the dependency of have metastore from the Presto Iceberg connector. And another ongoing project is about the Iceberg v2 support implemented by Beinan Wang from Alucio. This work is about that we can allow some row level updates and deletes in the Presto Iceberg connector. And finally, I'm also doing a task about the materialized view support of the connector. I also attach the link of the code base, the Presto Iceberg code base in this slide. So feel free to have a look of this code base and contribute to it. Or if you have any questions about it, you can just post it in the open source community. And that's all I want to talk about today. And thank you so much.
Fantastic, Junzu and Daniel. Thank you so much for the great presentations. Now's a good time to put in your questions and Q&A. We do have some. So let's go ahead with the first one. Pengfei, the first one's for you. So the question is around how do you compare your approach that you've put together with LinkedIn's transport? I think the question that is around what is called the Coral project, which adds transportable UDF support to Presto and a couple of other query engines. I'm not sure if you're familiar with it.
For the LinkedIn transport UDF project, it supports to It provides a common protocol to write UDF and automatically translate it into UDF in different native UDF in different engines. But our case is that we need to migrate our workload from Hive Spark to Presto. Our users already write their UDF in the Hive UDF, so we need to support the Hive UDF wrapper features. Yeah, but I think the transport linking transport feature is a very good feature. And for the new we can use it in ByteDance, I think. Yeah.
Okay, thank you. So it looks like it's orthogonal, right? So it's in addition to the work that they've done. In their case, they actually translate the actual UDFs, right, to be runnable on Presto, and your approach is a little bit different. So thanks for that. Next question is Daniel. Next one's up for you. How did you decide on 2 intermediate levels in Iceberg, the manifest list and the manifest? Why not 3 or 1?
So that's a good question. And if you actually go and look carefully at the spec for Iceberg, you will notice that it actually used to be 1. And that was kind of early on in the Iceberg spec. And now there's 2. And there's actually good reasons why we have 2 as opposed to 1. 3 may be just kind of unnecessary, though eventually, you know, if we get to the point where the data sets are so immensely huge that you need another level of indirection, that may be possible. But the reason why 2 versus 1 actually goes to one of the points that I had on my slide, which is like the low right amplification. And the idea being that when you have multiple jobs that are working against the data set, potentially even in multiple engines, they may all be producing data and writing it into the data set. And what you want to do is you want to have as little churn of the metadata as possible. So if I'm producing new data, I can write out a new manifest and then add it to the manifest list and then commit the table. And that's a much smaller operation than trying to rewrite the entire set of data files for the entire table every time that you're trying to perform one of those operations. So that's kind of the reason for the 2 layers of indirection there. If you just had 1, you'd have to do a lot of rewriting for every commit. This actually really reduces that. And then, you know, if you think about being able to kind of restructure that in different ways, there's a lot more opportunity if you have more levels. If you have even more levels than that, then you can get into problems with just like you have so many of these metadata files to scan, and it may be unnecessary given the size of the actual tables and volume. So like we're seeing tables that scale very well up into the tens of petabytes and higher. So if we get into the exabytes, maybe there's a 3rd level that may be necessary, but it seems unlikely at this point.
Yeah, it's very interesting. The ingestion dimensions and characteristics sometimes are very different from the consumption performance improvements or efficiencies, right? And so it's hard sometimes to make these calls because what works better for ingestion doesn't work better for querying. And if you create more files, you're just going to have to scan a lot more, and it reduces latency, or increases latencies rather, reduces performance query time. So hard decisions to make.
And Iceberg addresses some of the concerns about like that level of metadata by allowing you to kind of rewrite your metadata in different ways. So you can actually compact your metadata.
That's right.
You can restructure it to optimize for the read or the write patterns. There's a lot of flexibility there.
Great. I think there is one more question. Maybe Daniel, you can take it first, and maybe Chanshu, you can add after that. So what's the unique advantage of schema evolution? The feature set commands look similar to standard table management operations. So data lake versus database.
Yeah, so I would say that like schema evolution is not a new concept. If you were coming from the traditional relational database, like operational data store world, yeah, it seems like table stakes. The Postgres, of course, has supported that for basically ever. But at the same time, like the key advantage is If you don't have true schema evolution, like I mentioned, you can run into real problems with your data set. And these are really big data sets. It can be very expensive, both from a human time as well as compute time, to correct for mistakes that can emerge from improper schema evolution. So the key advantage here is that that it's safe with Iceberg. It's going to prevent you from doing bad things. And you don't run into the scenario where ultimately you get into this state of either having incorrect data or having systems that can't interoperate with your data set anymore because you've evolved it in a way that can't be handled by one of those engines.
Chunzu, anything more to add to that?
Yeah, I can just add a very short answer to it. Just at Twitter, the case is that the data set is the data set is too large that cannot be handled by say a relational database like MySQL, right? So in that case, we have to store the data set in HDFS or GCS. In that case, we need to have another layer that can act as provide some similar mechanism to the traditional database. And I think that's what exactly the Iceberg is doing nowadays. That's why we really like the Iceberg feature at Twitter.
Yeah, that's a great point. And one more thing to add in general is the table formats in Iceberg became so much more important because cloud stores are HDFS, at least maybe you can mutate, but cloud stores are immutable, right? The objects are immutable, and so what that means is that you can't really have upserts or updates kind of directly on it. And so to get true data warehouse workloads to be running on the lake, you need a table format, a transaction manager, whatever. There's new terms that are emerging for the layer, but it's a very important layer, which then allows for the schema evolution so that you don't have to constantly, today, if you don't have it, you have to keep syncing back with Hive Metastore, and you might be out of sync, right? And when columns get added, you may not actually see them when you query it. That is creates a bad experience for the end users, right? And so this really kind of enables new workloads that weren't possible before on the lake that are just bread and butter for the data warehouse or the database side. So great to see this evolution. I think it's we'll continue to see innovations on this over the next few years. So I think those are all the questions. Thank you so much for the great questions, folks. And a big thank you to our presenters today. Peng Fei from ByteDance, Daniel, Tabular and Iceberg, and Chunzu from Twitter. Thank you so much for the presentations. Appreciate it. One last shout out. We have PrestoCon coming up. Registration is open and would love for all of you to be part of that. Check it out at Linux Foundation events, and see you at the next meetup. Thanks, everyone. Cheers. Take care. Bye-bye.